Hello, greetings, my friends. This is Dr. Mohammed Nizami from Jerash, Jordan. That's the ancient city back there behind me. Welcome back to my direct RF sample radio receiver system design and architecture. We're talking about RF to bits, and this is part 8. So I welcome you to this session. Please, if you're just joining in here in this session, please go back to the previous sessions. I have, this is part 7, 6, 5, all the way to part 1 are listed on my YouTube channel, this channel right here. Please go ahead and sign up if you like. Subscribe to the channel. I would appreciate it. Now, last time we've been covering. Okay, this is this is just for those of you that may stumble onto the slides just to find out their way to the video lecture. So I have an outsourcing service for those of you in North America and Europe and India and the Middle East as well. If you need any assistance in RF board level designs, or if you have a product, you have an obsolescence board that you need to modernize, please reach out to me at this phone number or this email or on LinkedIn, and she'll help you. I start out with concept, specifications, system modeling, then schematics, PCB, and produce PCBA, and work with you as well in the design all the way through production. So last time, this is what we have been talking about, and we did cover all these things in here. Refer back to part 7. But what we're going to talk about today is we're going to continue with the RF sampling ADCs, and then talk about the nonlinearities performance and how does that impact the receiver design. And then I'm going to go through 2 examples, okay, that I have. One is a 2800 S-band receiver, and the other one is a 28 gigahertz millimeter wave receiver system design. So I'm just going to run those on system view and just show you how you can actually manipulate all these things. Now, realize up to this point, we have not incorporated spurs and harmonics due to the interleaver process of the ADDs, as those spurs are not incorporated yet. So we've got those spurs that, and the issue with them is that they fold back, and once you go through the digital down conversion and the decimation, they move around, so you have to keep track of them, and that's why we're going to talk about the RF direct sampling, RF system frequency planning, and that's what replaces really the conventional receiver system planning that we used to do. Remember the what IF that we used to use to locate select an IF for a heterodyne receiver that is free of any spurs and harmonics. In our case right now, we don't have LO, so we don't have MLO plus minus N RF signals, and of course the harmonics and spurs of the LO and the incoming receiver. So we replace that in the direct conversion, direct sample retriever with the ADD nonlinearity performance in terms of second order harmonic distortion, third order harmonic distortion, interleaver spurs, sampling signal spurs, images, and so forth. So we're going to talk about. And then I don't think I'll get to these 3 parts here. We're going to leave these to second lecture. All right, so let's just refresh your mind to this. What we're doing is basically we have an RF front-end receiver that is just simply made with filters and amplifiers. We may have a duplexer in here, depending on the duplexing scheme, whether it's time division duplexing or frequency division duplexing. But we don't have any frequency conversion, as you can see. The frequency we go in is the frequency that hits the A to D, actually. And then, of course, we have the DSP section here. So, and the A to D that we have been talking about, if you refer back to the last session and the ones before, is an A to D that encompasses several DSP functions. Basically, once we digitize a signal in here, usually its center band or its carrier frequency is much larger than FS, or it could be smaller than one half of FS, meaning the incoming signal is in the first Nyquist zone or other Nyquist zones. Either way, the signal itself in the digital domain, if you take the FFT of the signal that you're capturing, it will not be sitting at baseband, meaning 0 Hz. So what we need, the first thing we need to do is use a numerical controlled oscillator in the DSP section and go ahead and multiply a DDS sine wave and cosine wave. Of course, it's a quadrature because this signal in here is a complex. Or even if it's real. I mean, this is real, but we're gonna we're gonna make a complex out of it, and that's when we multiply it with an NCO using a numerical multiplier. Okay, and then of course we low pass that because as soon as you do that, things will shift back close to the desired band, and then of course we're way oversampling than the bandwidth that is required or the number of minimum samples per symbols. So what we do then is we decimate by M, okay, and then we pass it along to the FPGA that has the modem functions, that does the demodulation. In the transmitter section, which is not covered right now, we do exactly the same thing. So we go out the other way around to a DAC, and instead of decimation, we have interpolation, meaning we increase the sample rate so that we could spread out the images far out so we can do transmitter filtering. All right, so today I'm going to talk about the thing we have left at from last time, the nonlinear performance of the A to D in terms of Spurs that belongs to the harmonic distortion, second order and third order harmonic distortion, and then look at the second order and third order intercept points. So the A to D itself, we model it, or even the whole front end of the receiver, we model it as a nonlinear function that is made of these things in here. Okay, so we've got AX to the cube plus BX second plus C. Okay, and then what we do is if you excite this receiver or A to D by itself with two tones, and with two tones, that's sine of A and then sine of B, you're going to end up with sine of A plus sine of B to the power 3 and then to the power of second. So you're going to end up with with a polynomial that is going to include plus minus powers of the sine waves, and you're going to get twice the frequency, 3 times the frequency, and then the inner beats and the summing and subtraction between them. So you can refer back to any receiver books, and you will see how this the phenomenon is actually treated mathematically, so you would understand the mechanism behind that. But to make the story short, we end up, if we put these signals in here, what we're going to get out is this here. And of course, the desired signals is F1 and F2. So we're going to get F1 and F2. And usually, if you use a filter to filter it, so we can get rid of everything else. We can get rid of all these things. And they're color-coded in here, meaning that this one in here is due to the second harmonic, due to the terms that come up from here. And there are terms that come from here because this is x to the 2 and x multiplied by x to get to 3 order. So we got these here, and we got the subtraction, which ends up being at low frequency in here. And then the third order from this term in here, we get these here, okay, 3 times F1 and 3 times F2, F1 and F2. And this one, of course, 2 times F1 and 2 times F2, plus the other terms, which is the F1 plus F2. And F1 minus F2, we are going to end up here. It's going to be a low frequency portion. So in the third part in here, you can see that these terms produce other terms that are so close to F1 and F2, like twice F1 minus F2. That's just going to be the spacing between these two tones. The spacing in here, there you're going to have two terms. One is above and one below. And these in here, basically the relative strength of this component in here, that is due to twice the frequency minus F1 and twice the frequency of first one minus F2. These are going to be the third order intermodulations because they're really because of three frequency components, twice here and one here, okay? And these are difficult. These are important because these are difficult to remove. You can't remove them really, unless you have a very extremely sharp filter. I mean, even if you do, there's going to be two other frequencies for broadband signals that are going to be close in, even in band. So it's impossible to remove this. And all we can do is come to the receiver in here and just design it so that this uh, this nonlinearity term in here is not significant to the point where it impacts the signal to noise ratio or Spurs free dynamic range. Okay, the other ones in here we can easily remove them, and even this one. Okay, so these are easy to remove. These are hard to remove. So we've got the third order inner mods in here. There, these here. And then we got the distortions due to the third order and second order products are in here, okay? All right, so now the thing is when you have the signals in here, if you there's a proportionality between the relative strength of the third order and even the second order, um, the second order inner modulations, and their strength is proportional. Usually, there is a relationship where one will increase, has a 3-to-1, and one has 2-to-1 relationship. Okay, and that has to do with the fact that you increase F1 and F2 by 1 dB. How much is this going to increase? These terms in here, and that can be observed by observing sweeping the input signal in here, you sweep it and you monitor the output, okay? And of course, this one in here happens to be that's normalized by the gain. So the power in the linear region, you got power in, power out. Okay, so we subtracted the gain, normalized it to the gain. So what's going to happen is your input signal itself, as you push more and more signal, you're going to end up being linear until a point where it starts to clip and saturate. Saturation comes basically from these devices and from the ADD itself, because the ADD, remember, you have the full scale, and that's the all ones, and that's going to saturate, okay? And of course, in the ADD in here, you do have differential drivers into the ADD. Those are treated nonlinear devices, just like the amplifiers, the RF amplifiers, and the front end. Those can cause that to happen as well. So one of the things that we define is we can record the second order inner mod and the third order inner mod powers, okay? And if you plot them, at some point when you get completely saturated, you can go back to the third order inner mod and the second order inner mod and draw a straight line, and that straight line will actually intercept the P in versus P out, okay, the transfer function of the whole system. And those interception points are called the second order intercept point and the third order intercept point. And they correspond to 2 points, which is the IP2, IP3, and OIP2 and OIP3, which is the input and output second order and third order intercept points. Now realize the second intercept point in here, this one in here, is way out there, much higher than the third order intercept point. This one, you reach it faster. So there's always this one here is the second order intercept point is way above the third order intercept point. There's also another early warning indicator of the nonlinearity performance of your receiver, which is the output 1 dB compression point or the input 1 dB compression point. And that is basically you go out to the saturation level and you back your input until you get to a point where the output compresses only by 1 dB from the linear expected output. And that point, usually right here, is called basically the 1 dB compression point, okay? Which means always, if you're giving that, you know that the saturation power is going to be 1 dB above that, okay? So realize this now. So in the ADDs that we have covered, usually we are giving these points in terms of two-tone test signals for a certain input. And the same thing for the RF devices as well in here. So now, now again, let's look at closer on this. So we do have the third order intermod and second order intermod when you feed two tones to the ADD or to the whole receiver. Now the ratio between the output of those two tones to the third order intermod is called IMD3, okay? And the second order intermod, which is due to twice F1 plus F2 here, you can reach out to this, and that's IMD2. Those 2 points are important, and they're usually given in the specification data sheet of the RF sampling ADD. Now, why is this important is because of the following. First of all, the third order intermod, when we have a channel filter, this one in here, this is, let's say that this is the input response of the ADD or the receiver, the overall receiver. You can see that if you want to try to cover all the spectrum, that eventually when you run frequencies here, you're going to end up with these second order and third order intermod products, and those are going to alias back in here into the DSP, so into the baseband, and going to be distortion or reduce your Spurs free dynamic range. So you can't really do anything about these other than manage the linearity of your system overall, so that this here and this here is at least hitting the noise floor, is below the noise floor of the ADD. If they start rising above the noise floor of the ADD, then these are an issue. Right away, you're going to start your dynamic range of the receiver, and the ADD is going to be reduced. And so if you have a channel filter, okay, you can reduce the level of the intermod 2 and the third order intermod, but not the third order intermod. I mean the third order distortion, harmonics, sorry, which is due to the 3 times this frequency and 3 times that frequency, and then the interaction between them, okay? All right, now turns out there is a relationship. So what we do to find out the output third order intercept point here, the output, and the output second order intercept point, we need to find out what the RF level and the both the intermod values in here. And there's an equation, a simple equation, which is the output third order intercept point is really output, sorry, is equal to the output power plus the intermod by 2. So we go back to this, we measure this, we divide by 2, and we add it to this output frequency. And that gives us basically the output third order intercept point, okay? Or the other way around. If we are giving this here in the specification sheet, for a certain output power, we can find out what the intermodulation, third order intermodulation level is. That's these guys. So you could come in here and say, I want this to be 70 dB. So 70 divided by 2, that's 35 dB. So add that on top of the output. That should be your output intercept point, third order. Okay. Now, if you have a cascaded system, of course, when you have a system like this, you have a cascade of those. Every one of these has its own um, third order insert point. And so the overall combination of the third order, the overall total is equal to this equation in here. So you can see that it's really 1 over all of these, but at the end, you're going to take 1 over the whole thing to get to this total. But you can see that it's the last stage plus all the previous stages weighted by the gains. So you can see how this is. And that's basically, we're going to go to the system view, and that system view will do these things for us automatically. So when we're just gonna as you can see that like in this case and this in here. So you can look at the chain. This is the S-band receiver, and you can actually compute the third order input and the output third order and the cumulative gain for um, this system in here. Okay, because a lot of times we have many components and we can't do it by hand, or we can run it using MATLAB or now. Of course, now this is talking about the output third order insert point, but what about the input insert point? We have to back behind the device, find out what was the intercept point on the input. Well, all you need to do is just subtract the gain because really it compresses by that much. So, and the cascade of the overall combination of a chain of receiver components is computed by this here. I put a note in here that the output third order intercept point usually 10 to 12 dB higher than the 1 dB compression point. So what that means is that this point is usually above this point by 10 dB. So it's 10 dB in here. So if I tell you that this device has a 1 dB compression point that is plus 15 dBm, right away the third order intercept point output on the output, you can't exceed more than 25 dB amps, okay? That's just a rule of thumb. And you can go back to grab any data sheet for an amplifier or mixer, and then go and check yourself, and you can see there is really a relationship that is exactly equal to that. This is verified. And you can mathematically, if you go back and look at the receiver design books principles and from this equation here, yeah, this actually you can conclude this term in here is true. Okay. Now, what about the second order intercept point, the output second intercept point? Same thing. Okay. It's really the output plus the second order mod on the second order mod. So we do what we do from this test. We look at the power of F1 plus F2, which is the ENOB mod second order, and the output intercept point will be just the output power of this plus this magnitude in here. Okay, so that's pretty simple, as you can see. Now, the overall combination of series chain of nonlinear devices for the receiver is computed as this, and it's proportional to 1 over square root of the OIB2, which is the output intercept point second order. On the input, all you need to do, this equation here, find the input, all you need to do is just subtract the gain of that individual stage. Let's do a numerical example in here. So this I took from one of the data sheets or the app notes. I forgot which one, but either ADI or TI. So we have a device, okay? In this case, it's an AD, RF sampling AD. And we come in and we put signals into it. And then, well, this is actually the complete receiver. It's not just the ADD. So what we do is we measure the input in versus input out, and it's normalized, meaning 100 dBm gives you 100 minus 100 dBm. Okay, so the gain is being taken out of this here, and then of course they measured also the second order second order inner modulations and the third order modulations, and they measured the noise floor. This here is green light is the noise floor. Now, as long as the second order NMRs and third order NMRs are below the noise floor, we really don't care. And you can see on this receiver in here that until you reach out to minus 60 dBm, you're not going to see any of these products. Okay, and even the signal itself, you won't be able to see it. So the signal itself, you will start seeing it when the input reaches more than minus 100 dBm. But the inner mods, you will not see them until you start reaching out. The first one is minus 60 dBm. Okay, and that's the second order inner mod. The third order mod, you will see it later. So in this case in here, the second order inner mod dominates over the third order inner mods. Okay. So now the Spurs free dynamic range 2 and Spurs free dynamic range 3, these are really a measure of where how many dBs below the output of the ADD is the distortion due to the second order nonlinearity or third order nonlinearity. Like in this case in here, you can see that really the Spurious free dynamic range due to the intermodulation 2, that's just this point in here, which is minus 100 dBm, subtract from this point in here, which is literally minus 30 dBm. So that's about 70 dB. So you can see that the Spurious free dynamic range of the overall ADD is really, or this receiver, is 70 dB regardless of the third order intercept point, because you're going to hit the second order distortions are going to start coming up at you way earlier than the third order. This one here is about minus, I would say that's about minus 35, and until minus 20 dBm on the input is when you're going to start seeing the third order intermods come up. So likewise now, of course, for the third order, we come in here, the output in here is minus 20, so we subtract from the noise, which is minus 100, and that's 80 dB. Okay, so this one is 10 dB below that. The OIP2, in this case, of course, if you go back to this equation and this equation, they're really all we need to do is that we come in here. What's the output at this point in here? That's minus 30. So we just add to it the IMD second, which is 70. And that's going to give you basically 40 dBm. The third order here, this power here is minus 20 dBm, minus 20, plus, now with this equation in here, we have to divide by 2, of course. So you divide by 2, and that gives you about plus 20 dBm. So you can see that the OIP2 is plus 40 dBm, and the OIP3 is 20 dBm. Okay? Now, in this case, we didn't drive far enough to reach out to the 1 dB compression point, but we can assume that the third order intercept, this one in here, is really above 10 dB above, like the note that I had in here, is 10 dB above this level in here. So meaning this one in here is above the saturation level, which in this case it would be about 10 dBm, okay, on the output. So that would be right here somewhere. All right. Okay, so the Spurious free dynamic range also is defined. We can define it in another equation also. Here's another equation that is also derived basically from the same thing. It's 2/3 of the third order intercept on the input minus sensitivity. Sensitivity in this case is assumed to be the noise floor in here, which means the SNR is 0 dB. Okay, if that's not true, then all you need to do is just add the signal to noise ratio to this point here. But this here will give you exactly the same thing as these two here. All right, so for right now, let's go in system view, and we're gonna do these two systems in here, okay, and you can see them in here. Let me, I forgot to put this in full mode. Okay, so we have a 28 mega 2800 megahertz, and we're trying to have an ADD which is with this specification here, 14 bits. The full scale is 2 volts, okay, and which corresponds to about 4 dBm, I think, or we'll see in a minute. And the input impedance of the ADD is assumed 100 ohm, okay, and the Spurs field dynamic range is 77, SNR is 63. These are taken from data sheet, okay. So first thing is we need to do is we have to match from 50 ohm to 100, and that's with the 1 to 2 transformer in this case. And this here is very critical, and there are many app notes on trying to build the interface between an ADD that is 100 or 200 ohm to a 50 ohm system. And so some cases they use double balance in here, okay? So we come in single-ended, and we have to end up double-ended into the ADD, and in system view, the ADD is a single-ended, so I have to create like this where I terminated the other one, okay, which is still valid. Okay, so let's look at this example. So we have a desired signal. My desired signal is minus 100 dBm at the antenna, and assume the antenna is 30 dB gain, dBi. The desired gain, of course, is the desired input signal will be minus 80 dBm at the input of the receiver, okay? And the maximum signal level, let's assume that it was minus 40 dBm, okay? And I'm giving specifications in here that is the signal itself is centered at 2800 megahertz with 100 megahertz bandwidth. And the ADD is 3 gigasamples per second. Receiver chain is 2 dB basically. That's ahead of the ADD, okay? And the SNR required is 10 dB. So quickly, if we run through some of these equations that we have covered in the previous sessions, the first thing I want to do is where is the quantization noise floor of the ADD, given that it has these specifications. Well, that is here is really, first of all, what I do is calculate what is 2 volts, convert that to RMS and then to dBms, and that turns out to be plus 7 dBm. That's the full scale of the ADD. Now, below that full scale by the SNR, which is in this case right here, which is 63 dB, that would be my noise floor of the ADD. So minus 56 dBm is where I'm at the noise floor of this. Now, right away, immediately, like I showed in the last previous sessions, then my thermal noise required at this point, regardless of the of how big the size is, I want to make sure that my thermal noise that is represented right here, which is minus 174 dBm per hertz, when it gets to here, it's at least 10 dB above this level. So at minus 46. So right away, then what that says, I can size up the receiver, the overall receiver gain, which means I'm coming in here, I'm saying minus 174 dBm per hertz. I have to add to it, of course, integrate over the 100 megahertz bandwidth, okay, plus the noise figure, okay, and plus the gain, and that should equal to minus 46 dBm, which is the thermal noise in here. And that what tells me that the receiver gain has to be 46. So let's make it 50, okay? Let's put an extra 4 dB in there just so that we can, so the overall receiver gain in here from this point to this point has to be 50 dB. Now, then the next question is, we have the minimum signal. I'm saying here that the minimum signal is minus 110 dBm at the antenna. Of course, it's minus 80 dBm at this point in here, okay? So what that is, the minimum signal, that has to, when it reaches to the ADD point in here, it has to be above the thermal noise by the SNR, which I'm giving in here. I said the SNR has to be 10 dB. So therefore, then right now is I could say the minus 174 dBm per hertz plus the integrated over the full bandwidth, add to it the noise figure, add to it the receiver gain that I assumed in here, and an additional 10 dB for SNR, then I get minus 32 dBm. Automatically, that is the minimum signal at the ADD that I want. So that is really the minimum desired level, signal desired level range in here. And then, so what is the noise? Of course, thermal noise is minus 174 integrated over 100 megahertz plus the noise figure plus the receiver gain, which is minus 42. So I've got the noise at minus 42. I've got the signal at minus 32. Okay. I've got the gain 46. Okay. I've got the full scale at 7 dBm. Okay. So what is the maximum then signal that I'm going to get here? The maximum signal is we want to make sure that we don't exceed the full scale level in here by a certain margin, which is due to peak to average ratio, and we throw in 1 dB as a precaution measure, okay? And that you have to refer back to the equations that I used before. What that says is that, okay, if I have 7 dBm and my peak to average ratio, here it is 8 dB, that has to do with the type of signal that I'm receiving. Okay, the modulation, whether it's OFDM or QPSK, PSK, so whatever, it turns out it's minus 1 dBm. So that ADD has to withstand between minus 32 dBm to minus 1 dBm. And of course, we know that its range is from 7 dBm or from this level in here, from minus 1 dBm, all the way to the quantization noise, all the way to the thermal noise, which is this. We know that the dynamic range in here is 45 dB, okay? Yet I'm saying the signals are even smaller. So we're centered really good for the ADD. All right, so let's go to the tool and build up the system. So I put in 3 devices, and let me shift over to the actual circuit. So here's the system block. And what I did, I picked up a device, which is CMA_5043, okay? That has these characteristics, okay? And then I repeated using this here, and also here. Of course, the gain, each individual device is 18.4. And to control the overall gain to be 50, I threw in these pads, this one in here, there's one in here, there's one in here, okay? And so these are used to control the gain, okay? So, okay, so then what I do is I run this, and the first thing I do, let's go back, let's see, is what this is, this showing you the desired channel power, which I'm starting out at minus 80 dBm. Okay, so at this point, the desired channel power is the red trace in here, okay? And then the cumulative gain, okay? And then the cumulative noise figure, okay? So, and then these are the stages in here. So this chain in here, this chain in here is actually now, when we sweep it, I have this behavior. And so we can go to any of these stages and find out what the system response is at that point. So we start out, the input is minus 80 dBm, and right at the ADD output, we can see that the signal is minus 30. And that's, now if you subtract minus 30 from minus 80, that's 50 dB. And that's really the gain that we intended for this receiver. Now the receiver in here, of course, it has no AGC, automatic gain control. So that minimum gain, and we can decrease it right now. But in real life, you have to decide on your system what should be if there is a need for an AGC, okay? The next thing we look at is the minus 80 dBm at the input. The output is minus 30 dBm. That's at these points, okay? And that's if you go back to our calculations in here, hand calculations, and that's what I really wanted to see. So we are at 2 dB above this minimum number, okay? All right, so that's all right. And then the noise figure, or overall noise figure is 1.282 dB, okay? Now, let's go further and, of course, look at the input and output third order intercept points along with the cumulative gain. And you can see that they are right here. Okay, so we've got the input one, third order input one is minus 21, and the output third order one is 28. And of course, the difference between them is really the gain, which is 50 dB. The SNR, you can trace back. So let's pile together the desired channel power, the carrier noise power, uh, carrier to noise ratio, and the cumulative gain. And we can see that at the beginning, we have SNR of 13.8, about 14 dB of noise figure, because my noise at the input is minus 94 dBm. And why is it minus 94? Well, that's because when I set up my measurement system for this, I set it up for 100 megahertz. 100 megahertz, that's, if you take the log of that, that's 80 dB. So 80 dB from 174 dBm per hertz, that's really what you're going to get when you integrate over the full 100 megahertz bandwidth of thermal noise. You're going to get minus 94 dBm, okay? But that, because the receiver has 50 dB gain, by the time you get to the receiver, the noise power will be 44 dBm, okay? And so you can see that the signal to noise ratio is 13.826 at the input here, but as right after the ADD, it is actually 12.581, which is really good. We only lost a half dB of SNR because the noise figure is superior, and the ADD that I'm using is really is an expensive one. It's 14 bits. You can see that the signal to noise ratio is in the 63 dB, and that's why the overall design is good. Now, for the same system, what I'm going to do to check the nonlinearities is I'm going to put two tones on the input. So I'm going to put two tones. One is at 2800 megahertz minus 5 and one 2800 plus 5 at minus 42. And the reason I put them at minus 42, I don't want to put them very small signals, because you can go back and look at the ADD at the complete receiver. Okay, this is the sweeping the frequency. There's one that should display the. Okay, well, anyway, we'll get to that later. Okay, so we're going to come in here and we're going to run this system and see the inner mods that are going to come out. So, and of course, if we look at this, so I'm going to put in two tones, as you can see here, minus 40 dBm each, okay, spaced at 10 megahertz apart. And so the reason I put minus 40 is because I want to be right here somewhere when the nonlinearity is starting to happen. This is really what this is. This is sweeping the front end of the receiver versus the output. And the output is going to saturate at 7 dBm, which is the full scale of the ADD. So past around somewhere, let's see where it is. Past minus 42.2 dBm, I'm going to saturate the ADD, okay? And to the full scale, which is 7 dBm or 6.8, 6.9 dB in this case. So when we do that, we're going to get, okay, okay, so let's see. This is the input at the ADD, Okay, that's what's going into the ADD. And you can see right away that from plus 10 and here to minus 20, that's only 30 dB of intermod, third order intermod. And we're already at plus 10, which means if my ADD, the full scale is 7 anyway, so at this point, I've saturated the front end in here anyway. I'm 3 dB in compression as far as the ADD is concerned. And that's when you, of course, so the ADD itself, when you look at it, here's the output, and you can see that the full power is 7 dBm. These two tones are 7, are not 10 because the ADD can't provide more than 7. Okay, and the inner mod is 27 right now, the third order inner mod. And so you can also check for the second order inner mod. Okay, so that's one way to do that. The second example I want to look at is the 28 gigahertz. Now, the 28 gig, of course, the system that we just did, the input, let me just go back for a moment here. The input signal is centered at 2800 megahertz with a bandwidth of 100 megahertz, but the ADD was running at 300 megahertz. Now, remember from the last slides, we decided that we are sampling at a frequency that is higher than the carrier frequency. So therefore, we're going to get a digital IF, and the digital IF, of course, is going to be the subtraction between those two. Let me see. And you can see that the resulting digital IF is at 200 megahertz. And that's what we just computed the formulas. That's where you're going to your digital IF is going to be, and that's what. So you need a numerical controlled oscillator to get you to baseband from here on, because the resulting digital IF is not at 0 hertz. It's at 200 megahertz, which is a 3000 megahertz minus 2800 megahertz, which is 200 megahertz. Okay, so let's do one right now that is different, so that your signal is not sitting below the first within the first Nyquist zone, and that's basically I have a 28 gigahertz signal at minus 80. Okay, so let's go back here. So we did all of this. Okay, so we're going to go to the second example, which is this. Okay, and this example in here is a little bit different. So we have a 2800 gigahertz with 100 megahertz bandwidth, and the ADD is running is at 12.8 gigasamples per second, okay, in here. And the SNR is not as good as the other ones because obviously this is much more higher frequency ADD, and this is based on the Teledyne ADD. I forgot which one it was, but we covered it before. And this is, of course, 50 ohm right now, the impedance for this. And so therefore, we cannot use transformers in here, but we do need some kind of matching, but I'm assuming that it's 50 ohm. So right away, this system in here has no balance because at these frequencies over this bandwidth, we can't do that, okay? So let's see. Now let's do a little computations. So basically what I'm going to do, minus 80 dBm. The ADD is with this specs, and the range is 1 volt for the full peak. So therefore, the full scale for this device is plus 4 dBm. So the first thing we want to do is giving that you have an SNR of the SNR for ADD is only 38 dB. So that means the quantization noise of this guy is at minus 34 dBm, which is very critical because that's not a whole lot of dynamic range. Okay, and the full scale is plus 4 dBm, and we have to back from that to say somewhere, let's say here it is. So the peak to average ratio is 8. We have to back to minus 4 dBm. So minus 4 to minus 34, that's 30 dB of dynamic range only on this. Okay. So the first thing we want to do is we want to because the ADD in here the signal to noise ratio is low, Now this receiver is going to have much more gain required than the other receiver. So let's see what we got. First thing we want to do is a thermal noise minus 174 dBm per hertz. Add the 10 log of the bandwidth, 100 megahertz. Add the noise figure, which is 2 dB. Add the gain. That has to be less than this number. That has to be at least 10 dB stronger than this, which is minus 24 dBm. Okay, which means that your gain has to be 68 dB. So let's make it 70 dB. So what we did is we went in. Now, if you look at these devices in here, this 27 dB of gain, here's 27, and here's another one, which is 27. These are based on an ADI LNA, which is ADL 8142, okay? And there's a whole bunch of pads between them to manage, control the level, okay? So right now, then the signal, minimum signal, with the required SNR, which is 10 dB, we need the minimum signal to be at minus 12 dBm for this device, okay? And of course, what that says is that the thermal noise minus 22 dBm. So we're at 10 dB below this, okay? So in essence, what we're doing really is this. So we have a signal which is sitting at 28 gigahertz. And the first Nyquist zone is 6.4 gigahertz. So when we sample this signal is going to alias all the way back to here, and it's got 1, 2, 3, 4, 5 regions to alias to get to the first Nyquist zone. Okay? So the digital IF would be this 28 minus twice the 12.8 giga samples per second, which means by the time it gets to here, and this range is from 0 to 6.4 gigahertz, it's going to be centered at 2.4 gigahertz. And at that point, of course, the ADD itself has this functionality, which here. So we use the NCO to digital down convert and reduce the sample rate to the appropriate sample rate that is at least twice the bandwidth. The bandwidth is 100 megahertz, so we need at least, say, 400 megasamples per seconds at that point. 400 megasamples per seconds, we're already at 12.8 gigasamples per second. So you can see how much decimation you have to do to get this to be that. And of course, now we have to filter so that we don't have noise folding or the images in here and spuriouses that we're going to have later on creeping in. All right, so let's look at the response. So I have this here. I ran it. The first thing is we can see the chain in here, the 3 amplifiers and the ADD, and we can see that at the input minus 80 dBm, okay? And I'm showing desired channel power, cumulative gain, and carrier to noise figure. Okay, so I'm not showing the noise power yet. We'll see it on the next slide. Okay, unless we could, let me just add that in there as well. So that is basically that's basically the carrier noise power. Let me see if that works. Okay, carrier noise power, there it is. Okay, so what I'm going to do right now is I have the signal at minus 80 and have the noise power at minus 94 dBm. And that's the noise power within 100 megahertz bandwidth, okay, at room temperature. At the output, the signal, the desired signal level, the desired channel power is at minus 22.4 dBm. No, sorry, minus 10 dBm. Here it is. And the noise is minus 22 dBm. The overall gain is 70. So therefore, this chain is verified. Then we go next to the output third order intercept point. And of course, we We have to also look at analyze the compression stages and so on. So there's so much stuff that you can do with this one. So next, I'm gonna go and check the nonlinearity of this. And I put in two tones spaced by 10 megahertz, centered at 2800 megahertz, and then let's probe in and monitor what the signal is at the output. So we're gonna come in here. So the signal into the A to D, that's what it is. Okay. So 2 and 3 at 2, it's 7 dBm, so it's full scale. Right? It's more than full scale because full scale is 4 dBm for this device, for this particular device. So we're already in compression without even getting to do the A to D. And of course, that's why you see that you have to go back and start looking at this system in here and manipulating the compressions so that by the time you get to the A to D in here, you don't have inner mods, okay? And of course, we're not doing that yet. So let's look at the A to D in. I'm sorry, right here. So that's the minus 50 dBm into the system. And let's see. Okay, the ADC in, that's what it is in here. So we've got very compressed. And the output, of course, of the ADD is this. So you can see that this is displaying the signal spectrum within the first Nyquist zone. So the first Nyquist zone is from 0 to 6.4, which is half of the sampling frequency. And you can see that all of these are images from harmonics and intermods that have folded back within the input. And we can zoom in to the desired channel itself and look at it, and you can see that 4 right here is 4 dBm, and that's full scale, meaning the A to D is clipping. Okay, and then you can look at the third order intermods in here, which is only minus 16.4. So it's about 20 dB third order intermod. Okay, and then you can start going back to the chain in here and start working on that thing in here. So all right, so I think that's what it is now. You can see that the output, of course, is going to have a noise pedestal, and the noise pedestal, you can trace it back to actually saying it's minus 174 integrated over 100 megahertz, plus the noise figure, plus the receiver gain, and that's minus 22.4 dBm. That's what this level is when your output is on. Now you could, of course, let me see. You could go in and reduce the signal level. I'm sorry, that's this here. And I think you can see that this is the ADC coming in. I reduced it to minus 65, for instance. And you can actually see that the input now, the inner mods are just barely above the noise floor. So you can see that they're just, this is minus 18, 2 is minus 20, okay? And so you can work that out. So that's what this says, and this gets us to the slide that I showed, either the third or fourth lecture, where I showed the, let me show this. So we have the ADD itself. We have to really look at it in terms of the overall receiver. We have a full scale, like in this case, 1 dBm, and we have a thermal noise level, minus 174 dBm per hertz. Okay, and so we have to design this receiver chain taking into account the broadband noise power and the bandwidth and the desired SNR to be able to optimally set the input range to the A to D. And this is, of course, all of this assuming that you don't have interference and blockers. And as soon as you get that, of course, boom, everything you built is just down the drain because, like in this case, for instance, it's displaying that this is your desired signal in the green. You got it, but then before you get to drive level, your blocker or the interference has clipped and has saturated your ADD. What do you do then? Okay, in this case, in here, I may not be able to filter because it's so close to the input signal. So what do you do in this case? And that's really an issue that we have to look at in the next sessions. That's where we look at the basically the inner mods that are going to creep in right here, that are going to creep in from the aliasing. So the inner mods are going to be alias back to the first zone. Okay, that's your desired signal region. And of course, if you have an FDD or a TDD, depending on which scheme of duplexing you have between transmit and receive, you're going to have also transmitter power leaks back at you. And then, of course, you're going to have the interleaver issues and other things. And that's when we have to start looking at how do we frequency plan this so that we don't run into a situation like this situation. Okay. All right, ladies and gentlemen. So this is it for this section. I'm going to post the slides on my LinkedIn, so keep an eye on that. But before I post them, I have to put some references where some of these graphs came from. They're all from manufacturers of the ADDs, out of sampling ADDs, all of them, literally, along with most of them, which is mine. But we also do corrections. Sometimes there'll be some errors that I have on the slides. So go ahead and reach out to me if you see anything that is in error, or if you have any issue with this. So next time we're gonna continue going further and look at the other issues that I just talked about. So we'll see you. This is Mohammed Nizami from Jerash, Jordan, wishing you good night, good day, whatever it is where you are. Thank you very much. Appreciate it.